Hi everyone. Welcome back to Dave's Maths channel. I'm your host David Tare, and today I'm going to talk about a topic that's very dear to me, namely number theory, because this is what I got my PhD in. Specifically, I have my PhD in algebraic number theory. There's a lot of different kinds of number theory. I'm not going to go into that today, but what is number theory? Well, I think Gauss called number theory the queen of mathematics. It's also known as arithmetic, by the way. Although I think that's a little bit of a misnomer because when we think of arithmetic, we usually think of elementary school arithmetic, namely, just grade school addition, subtraction, multiplication, and division. But actually, in number theory, the way arithmetic is used in connection with number theory can be a lot more complicated than that. So, what exactly is it? Well, I think the best way to begin is with what are called Diophantine equations because I think this is what number theory is really all about. There was a Greek mathematician, I think the third century A.D. His name was Diophantus, and actually he was born in Alexandria. I guess he lived in Alexandria, Egypt, but he lived. Actually, it's kind of interesting because there's a little problem about his life. I don't know if all these facts are true. I'll just read what it says here. His boyhood lasted 1/6 of his life, his marriage after 1/7 more, his beard grew after 1/12 of the 12th the more, and his son was born 5 years later. The son lived to half his father age, and the father died 4 years after the son. I don't know how accurate those facts are, but you can use all those facts together. You can turn that into a math problem. It actually turns out to be a Diophantine set of Diophantine equations that you can use to actually solve for how old he was when he died. And according to this problem, he was 84. I don't think we know exactly how when he was born and when he died. I've seen estimates from around 210 to 290. I mean, I guess he did live a pretty long life, especially for that time. But anyway, so what are these Diophantine equations I'm talking about? Well, the equation's kind of like the equation in this problem. They're equations with usually equations with integer solutions. I guess they've been kind of, that's not a rigid definition. Sometimes people say it's good enough to find rational solutions. Sometimes people are even more rigid. They say they have to be positive integers. I mean, in ancient Greece, nobody knew about any zero or negative integers, so a lot of people are kind of religious about having positive integer solutions. I don't really like that myself. I think zero and negative integers are just as legitimate as positive ones, but for a lot of historical reasons, a lot of people like positive integer solutions to problems. But basically, they're just simple equations, like algebraic equations with positive integer solutions. I think that's what a Diophantine equation is. And like I said, the integers can be generalized to rational numbers or maybe zero and negative integers. So those are basically what Diophantine equations are. And those are, I guess, the whole branch of math devoted to solving Diophantine equations. I guess that's what we all lump into what we call number theory. And number theory involves a lot of different areas of math. I mean, it's interesting because this all started with Diophantus in the third century A.D. At that time, most math, but the math that was needed to solve a lot of these damn Diophantine equations hadn't even been invented yet, and it wouldn't come until much, much later for a lot of them. Some of them are kind of simple, but most of them are pretty hard. And just to give you an example, I think Archimedes came up with this problem. Archimedes lived, I think, in the third century BC, in the 200s BC. He was probably the most famous ancient mathematician, at least ancient Western mathematician of all time. Archimedes was amazing. I mean, one of my favorite mathematicians of all time. Not only was he a great mathematician, you could maybe even call him a physicist. He was the one who discovered, the principle of buoyancy or the principle of, basically how you can measure volumes of irregular solids just by putting them in water, seeing how much water they displaced. And that, I mean, I'm sure you guys have heard this story. Yeah, but I might as well tell this story since I started talking about it. So you probably know the story where the king of Greece, I guess, at the time, wanted to know whether his crown was pure gold. He suspected that the people, I guess, who made his crown were cheating him, and they didn't make it out of pure gold. So they asked Archimedes, he was the greatest mathematician in Greece at that time, to figure out whether his crown was made of pure gold or not. And the way Archimedes did it, in order to figure that out, I mean, he knew the density of gold. So if he knew the volume of the crown, he could just, he could weigh it and then determine its volume and divide and get the density. He knew the density of gold. And if it turned out to have the right density, he would tell the king, yeah, your crown is made of gold. But if not, he would tell him it wasn't. But the problem he was having was, how did he figure out what the volume of this crown was? But then he was taking a bath one day, and he realized, I guess he got into the bath, there was water in his bathtub. He got in, the water went up because he went in, right? We all know that happens. But he was so what he figured out when he did that was that his body was displacing the volume of water in the tub, and he could measure exactly the volume of his body by how much the water went up. And he got so excited when he discovered that, he ran out naked. He ran out into the streets of Athens, I think, where he was living, and he started yelling, "Eureka! Eureka! I've solved it!" And so that's a very famous story, and that's just one example of some of the great math he did. So he was able to figure out how to determine whether the king's crown was made of pure gold. It turned out it wasn't, and I'm sure the king probably was very happy and probably gave him a lot of money or gave him some special honors and whatever. I don't know the rest of the story, but he was one of the greatest mathematicians and physicists of ancient times. And that was a big digression. I want to get back to the calorie problem. So Archimedes came up with a very, very complicated Diophantine equation. It wasn't even called a Diophantine equation yet, because it was 200s BC. Diophantus wouldn't come until about 400 years later. But he had this problem, and I don't even know the problem from the top of my head. It's a very, very complicated problem. He wrote it down. It involves cattle of different colors. There's like, I think, one, two, three, four, five, six, seven, eight different varieties of cattle, all different colors cattle. And he gives the proportions of each type of cattle in the herd. And then he asks for what's the smallest possible herd. This is supposed to be like the herd of Apollo or something. I guess the Greeks, they have their own pantheon of gods. Apollo was I guess, the god of the sun, and he had, these cattle. That was part of their legend. So in his problem, he said how many cattle Apollo had, and it had to obey these proportions. And it was such a difficult problem that it wasn't solved for 2,000 years. The first person to solve it, the guy I already mentioned, Carl Friedrich Gauss, he was probably the most famous mathematician of the at least up to his day, he was the most famous. Maybe either him or Euler. It's a close tie between Euler and Gauss. I think even today, most people consider Leonhard Euler, who came, I guess just a few decades before him, a Swiss mathematician. It's kind of a close tie between whether Leonhard Euler or Carl Friedrich Gauss. One of the two was probably the greatest mathematicians in the world. People debate which one, but most people agree it was one of those two. And I kind of did too. I don't know who I leaned towards. They were both great in different ways. But anyway, Gauss was the first person to actually come up with a numerical solution to Archimedes' cattle problem, and it was published, I believe, in a paper. I don't even know what year this paper came out. I think in the 1960s. And this guy actually wrote down the solution. And I think the smallest solution, I don't even know how many digits the smallest solution has. Something like 52 digits. I mean, it's an astronomical number of cattle. Suffice it to say, we couldn't make that many cattle on Earth. There aren't that many cattle on Earth. And, if there were, then McDonald's would have over 50 times, it would be like the number in the movie Sleeper. Maybe that's where Woody Allen came up with that number. I don't know. But, right now I think they've served something like maybe 300 billion hamburgers worldwide, but the number would be, like in the 10 to the 50th power. I don't even want to think about that. But anyway, it was solved by Gauss, and he used I don't even know. I think he used uh, um, algebraic number theory to come up with a solution. He was pretty good at that. You can do it with algebraic number theory. I could probably solve this problem myself. I don't feel like doing it, but I think I know the method that Gauss used to solve it. It's algebraic number theory, which is used for a lot of other Diophantine equations. I'll get back to that later. I want to talk about a simple type of Diophantine equation right now, linear Diophantine equations. These are equations of degree 1. Ax plus by equals c. I mean, I think you guys are familiar with these kind of equations. They're called linear equations because their graphs are a straight line in the Cartesian plane, in the xy plane. So here's an example. Here's a typical example you might see of a linear Diophantine equation. 87x minus 64y equals 3. How would you solve it? I mean, this is a little weird too, because you're always told when you learn algebra you need two equations to solve two unknowns. Here we only have one equation and two unknowns. And actually, this is another characteristic of Diophantine equations. I mean, the fact that the solutions have to be integers reduces the number of solutions. So if you were just looking for real solutions of x and y, there'd be infinitely many. It would be the whole line, right? Any point on that line is a solution. But since we're requiring that the solutions be integers, I think there's still infinitely many solutions, but they're discrete. And you can actually write down a parametric set of equations, which they do in the middle of this picture, x of k and y of k. And it turns out k can be an arbitrary integer. And you plug in any integer value of k, and this will give you the possible values of x and y in terms of k. This is what's called a parametric set of equations. If you were graphing these on a line, you get a bunch of equally spaced points on the line. And how would we solve this equation? I mean, actually, it turns out there is a really nice method for solving linear Diophantine equations. It's called Euclid's algorithm. Again, Euclid. Well, this is another famous Greek. So I have to explain to you Euclid's algorithm. So Euclid's algorithm is actually a very general algorithm. It's used to find the greatest common divisor of two integers, or GCD. You probably know it. Maybe you know it's the greatest common factor. But you're given two integers, say 87 and 64. Those were the ones we started with in this equation. So what we have to do is we have to apply Euclid's algorithm to find the GCD, but we have to do a little bit more than that. We can't just find the GCD. The GCD turns out to be 1. 87 and 64 are known as coprime or relatively prime integers, meaning that the greatest common factor, the greatest common divisor of those two numbers is 1. And this is how you prove it. You use Euclid's algorithm. So, you write 87 as a multiple of 64 plus, you just keep dividing and finding the remainder, basically. So 64 goes into 87 once, leaving a remainder of 23. And then you make 23 the next quotient. So you have 64 is 2 times 23. You do the remainder again, 18. You keep replacing the remainders with the quotients and the previous quotient with a dividend. You keep going like that until you're left with 0 at the end for the remainder. And then with the last number you're left with, the last quotient you're left with is the GCD. That's how the Euclid's algorithm works. But there's also or the Euclidean algorithm. There's also an algorithm called the extended Euclidean algorithm. You actually have to kind of backtrack and we have to wait 1 is something. So in this case, 1 is like 3 times 1 plus 1 times 2. But we're not done. We have to keep backtracking. And they do this here. So you want to write 1, the GCD, as a linear combination of the numbers you started with, which were 64 and 87. And if you use the extended Euclidean algorithm, when you keep backtracking through all the work you've done before, you find that 1 in this case is equal to 34 times 64 minus 25 times 87. So now you have to remember these numbers 34 and minus 25. And the last step, I guess I have to go back to the beginning here. So remember those numbers, 34 and minus 25. So now you have 87x minus 64y equals 3. Now all you do is you multiply 3 by the numbers that we were left with at the end, which were 25 and 34. I guess minus 25 and 34, you have to switch signs around. But anyway, so 3 times 25 is 75. That's where the 75 comes from in the formula for x of k. And then 3 times 34 is 102. That's where this minus 102 comes from. So this is called the extended Euclidean algorithm, and you can use it to solve any linear Diophantine equation. Pretty remarkable. So that's how to solve linear Diophantine equations. So, but right now this is still kind of ancient math. Um, and then this is just written out. You can write a computer program to do this, and people do this all the time. The Euclidean algorithm is used all the time by computers to calculate GCDs and extended GCDs. This is just kind of a symbolic way to write everything down. And this is the extended Euclidean algorithm. And then, okay, so that's just one example. Another example, I think I did a video on this a couple weeks ago. This is how to find Pythagorean triples. This is actually another Diophantine equation. A squared plus b squared equals c squared. That's the equation. And I'm sure you guys are all familiar with this formula. This is nothing but the Pythagorean theorem that says, a squared plus b squared equals c squared if you have a right triangle with legs of sides a and b and hypotenuse of length c. Everybody knows that. You learned that in grade school, probably. But there's more things of interest than just that. What if a and b, c are required to be integers? Then how do you find all solutions where a, b, and c are integers? Well, this slide shows you how to do this. This slide is actually if you look at this right triangle in the middle, they say a equals m squared minus n squared, b equals 2mn, c is m squared plus n squared. So you just pick any two arbitrary a pair of integers, m and n. Usually we require they're both positive and that they have opposite parity. You don't have to do that. That's just if you want to make sure that their a, b, and c are all relatively prime, so you get what's called a primitive Pythagorean triple. But if you don't care about it being primitive, you can just take m and n to be arbitrary integers or arbitrary positive integers. Usually we'll let n be less than m just to make everything positive here. But if you do that, then you can actually you have solved this Diophantine equation, a squared plus b squared equals c squared. And the ancient Greeks knew how to do this. They did this themselves. And I have a whole nother video on this, so I'm not going to say any more about this. But you can get all Pythagorean triples this way. Pretty amazing. And now I'm going to get into some more complicated ones. This thing is called Pell's equation, probably the most misnamed equation in math that I know. Pell had nothing to do with this equation. I don't even know who discovered this equation. I think it was discovered, maybe it was the ancient Greeks, I think, were interested in this equation. But Pell didn't even discover the solution. Pell just wrote down, he was a historian of math. And I think he just translated some German work on the solution of this equation. All he did was translate the solution, but he got his name on it. I think that's pretty horrible that he did. I wish they'd change the name to whoever really discovered how to solve it. It's probably Gauss. I'm pretty sure it was Gauss or Euler, one of those guys. It was discovered in Germany, anyway. So anyway, it was not Pell who discovered how to solve this equation. I wish it wasn't called Pell's equation. But the equation says x squared minus dy squared equals 1. And here d is an integer. D is a positive integer, but it's usually we require that d is not a perfect square. Actually, if d was a perfect square, there'd be no solutions. It's pretty easy to see this, because if d was a perfect square, then dy squared would also be a perfect square. So you're saying that this difference between two squares is 1. Well, there's only one solution to that, 1 and 0, right? So that wouldn't even be an interesting equation. So we always require that d is not a perfect square. And it turns out that if d is not a perfect square, if d is any positive integer that's not a perfect square, I guess the first example is 2, then there's infinitely many solutions to this equation. And actually, there's a nice method for solving them. I think this is what Pell wrote about. And the solution involves algebraic number theory. This is much later math. This is math that wasn't invented, I think, until the 18th century. But I think Gauss figured out how to solve this equation. And probably some other people did before him. And just to show you, this is the solution. This is all what are called the fundamental solutions to Pell's equation for, I guess they call it K here. I don't know why they call it K, but K is really the same thing we call D in the previous slide. So in the left column, these are the values of D up to 20. Notice that we skipped all the squares. So yeah, you put 1 in here, but 2 is the first positive integer that's not a perfect square. And then it turns out that 3 and 2 is the smallest solution. 3 squared minus 2 times 2 squared is 1. Pretty easy to see. But if k is 3, well, then it turns out the fundamental solution is 2 comma 1. So 2 squared, that's 4, minus 3 times 1 squared is also 1. You can keep going. It turns out you can check these yourself, but these numbers in the right column, you can forget about the 2 in the middle. I don't even know what this means really. Well, I guess you need no, you don't need R. So just concentrate on the left and right columns of this table. The left column shows the value of D. They call it K here. And the right column shows the values of X and Y, the fundamental solutions. But like I said, there's infinitely many. And once you get one, it's very easy to get all the others. Uh, that's all I really want to say about that. The solution involves some algebraic number theory. You actually have to work with square roots and what's called a fundamental unit. Since I started talking about that, I might as well finish it. So 3 plus 2 times the square root of 2. So look at this xf and yf in the right column. So notice for instance, for k equals 2, then your fundamental solution is 3 comma 2. Well, the way you get all the other ones is you let rho, I don't know whether using this rho here, but rho, that's usually what you use for the fundamental unit. Rho is 3 times 2, 3 plus 2 times the square root of 2. And if you take powers of rho, you get all the other solutions. So you can square that. 3 plus 2 times square root of 2. If you square that, I think you get 17 plus 12 times the square root of 2, so 17 comma 12 is your next solution, and you can keep going as many times as you can. And you can do this for all of these numbers. And I think these solutions are really interesting, I think. I mean, people have solved this for k going into the thousands, maybe even the millions. It's easy to write a computer program to do this. But what I think is a little weird about this, notice that most of these solutions have pretty small values of x and y, fundamental solutions, xf and yf, but some of them are pretty big. Like look at 13. 13, the fundamental solution is 649, comma 180. I mean, it's a little strange that that one's so big, so much bigger than all the others. 19 is kind of big too. 170, 39. It turns out the way you get the fundamental solutions involves something else called continued fractions. And the way you get these fundamental solutions is you have to solve for the continued fraction of the square root of k. And I guess the reason why 13 has such a big fundamental solution is because the continued fraction of square root of 13 has a lot of terms to it, more than most of these other numbers. Anyway, I'm not going to say anything more about continued fractions. I'll probably make another video on that some other time. But, one thing I want to point out right now is that, you start with a simple Diophantine equation that, I mean, just something that, any idiot can think of pretty much. Even Pell, I think he was probably an idiot. He probably thought of this equation, and then he got interested and he translated a German paper on it. But it's a simple equation. I'm sure the Greeks thought of this equation. But the solution involves a lot of complicated math that wasn't invented until almost 2,000 years later. So that's what I find kind of interesting. And the last example I'm going to talk about in this regard, and this is probably the most famous one, Fermat's last theorem. I'm sure most of you guys are familiar with this. This is kind of like a generalization of the Pythagorean theorem. We know that x squared plus y squared equals z squared has infinitely many solutions, x, y, and z in integers. The Greeks knew that. But what if we let n be an integer greater than 2? What about x cubed plus y cubed equals z cubed? Does that have any integer solutions? Turns out it doesn't. What about n equals 4? X to the fourth plus y to the fourth equals z to the fourth. That doesn't have any solutions either. I think Fermat proved the cases n equals 3 and n equals 4. And he said he had a truly marvelous proof for all n greater than 3, all integers n greater than 3, but he said that he didn't have enough room to write it down. And he wrote this in 1637, I think. And for almost 300 for over 350 years, it was actually 1623, I think. For 350 years, mathematicians struggled to find a proof. And he said he thought it was a proof that wasn't known as Fermat's last theorem. This is another mathematical misnomer. I don't think it was really a theorem. I would be entirely amazed if Fermat actually proved it. He probably thought he had a proof, but I'm sure it was flawed. I mean, I think I'd be as amazed if it turns out that Fermat actually solved this in 1637. I'd be as amazed as that as I would if my glass flew up in the air spontaneously. I just don't think that's possible. So I don't believe that he solved it. Because, I mean, for mathematicians for almost 4 centuries tried to solve this equation using all the math they had available. Nobody was able to do it. There was even a French mathematician, I'm not even sure his name, but he was so sure that nobody could solve this that he even had a stamp made that said your proof has an error on page blank line blank. And he asked he had a student that wanted he asked to fill in the blanks. So everybody who came to him and said he thought he had a proof of Fermat's last theorem, he was so sure they didn't that he asked the student to go through these papers, find the errors, and fill in the blanks. And the poor student had to do that. But yeah, I mean, the first person to actually prove this was a British mathematician named Andrew Wiles. He didn't prove it until 1995. And I remember when he proved it. I was in graduate school at the time in Berkeley studying physics. It made the news. It was just an amazing discovery. Probably maybe the greatest mathematical proof of my lifetime. Probably so. And his proof was over 100 pages long. And it involved math that I don't even understand. It involved algebraic geometry. I tried to learn a little bit of algebraic geometry. It's hopeless. It's beyond, most of it's beyond me. The weird thing about algebraic number theory, most of it doesn't even involve numbers. I mean, the weird thing about all this to me is that the math gets so abstract to try to solve these Diophantine equations, which do involve numbers. That's why it's called number theory. But you end up using such abstract math and you use such advanced concepts like schemes and sheaves and varieties. I mean, these are names of some of the structures involved in algebraic geometry. I don't even know what any of those things are. Oh, varieties. I know what varieties are. At one time, I knew what a sheaf was. I forgot. It's a very, very horrible, complicated definition. I never knew what a scheme was. But you have to know about all that stuff just to be able to prove Fermat's last theorem, which Andrew Wiles did. Uh, um, and I think the last thing I want to say about all this, I just think it's really, really unfortunate. I think Andrew Wiles is probably one of the greatest mathematicians of all time. I mean, think about it. He solved an unsolved problem, a 400, almost 400-year-old unsolved problem in math, and frankly, nobody knows who he is. And I just think that's horrible. I mean, what kind of world do we live in if that's kind of true? I mean, I don't want to say any more about that, but you know, if I'll ever live to see an American stamp with a picture of a mathematician on it, I'll be happy. So I think that's the last thing I'm gonna say. Anyway, that's my talk. I hope you enjoyed it, and I'll see you next time.